Sound Basics Part 2 Introduction. Studying of a sound is a vast ocean and it ranges from simple to complex concepts. After knowing the simple things, it is necessary for us to understand the complex items, which form the larger umbrella of sound and its elements. We now arrive at what is probably the single most important concept for both understanding hearing and speech acoustics. The graphs that we have used up to this point for representing either vibratory motion or the air pressure disturbance created by this motion are called time domain representations. Sinusoids are sometimes referred to as simple periodic signals. The term periodic means that there is a pattern that repeats itself, and the term simple means that there is only one frequency component present. This is confirmed in the frequency domain representations in figure 3.10, which all show a single frequency component in both the amplitude and phase spectra. Complex periodic signals involve the repetition of a non-sinusoidal pattern, and in all cases, complex periodic signals consist of more than a single frequency component. All non-sinusoidal periodic signals are considered complex periodic. Figure 3.11 shows several examples of complex periodic signals along with the amplitude spectra for these signals. The time required to complete one cycle of the complex pattern is called the fundamental period. This is precisely the same concept as the term period that was introduced earlier. The only reason for using the term fundamental period instead of the simpler term period for complex periodic signals is to differentiate the fundamental period, the time required to complete one cycle of the pattern as a whole, from other periods that may be present in the signal. Example, more rapid oscillations that might be observed within each cycle. The symbol for fundamental period is to fundamental frequency. FO is calculated from fundamental period using the same kind of formula that we used earlier for sinusoids. The signal in the top panel of figure 3.11 has a fundamental period of 5 milliseconds for fundamental period 1 by 0.005 is equal to 200 Hz. Examination of the amplitude spectra of the signals in figure 3.11 confirms that they do, in fact, consist of more than a single frequency. In fact, complex periodic signals show a very particular kind of amplitude spectrum called a harmonic spectrum. A harmonic spectrum shows energy at the fundamental frequency and at whole number multiplies of the fundamental frequency. For example, the signal in the top panel of figure 3.11 has energy present at 200 Hz, 400 Hz, 600 Hz, 800 Hz, 1000 Hz, 1200 Hz, and so on. Each frequency component in the amplitude spectrum of a complex periodic signal is called a harmonic, also known as a partial. The fundamental frequency, in this case 200 Hz, is also called the first harmonic. The 400 Hz component 2 frequency is called the second harmonic. The 600 Hz component 3 frequency is called the third harmonic, and so on. Figure 3.11. Time and frequency domain representations of three complex periodic signals. Complex periodic signals have harmonic spectra with energy at the fundamental frequency and at whole number multiples of fundamental frequency 0, 2, 3 and 4, etc. For example, the signal in the upper left with the fundamental frequency of 200 Hz shows energy at 200 Hz, 400 Hz, 600 Hz, etc. In the spectra on the right, amplitude is measured in arbitrary units. The main point being made in this figure is the distribution of harmonic frequencies at whole number multiples of fundamental frequencies for complex periodic signals. The second panel in figure 3.11 shows a complex periodic signal with the fundamental period of 10 ms and consequently a fundamental frequency of 100 Hz. The harmonic spectrum that is associated with this signal will therefore show energy at 100 Hz, 200 Hz, 300 Hz, 400 Hz, 500 Hz and so on. The bottom panel of figure 3.11 shows a complex periodic signal with a fundamental period of 2.5 ms, a fundamental frequency of 400 Hz and harmonics at 400, 800, 1200, 1600 and so on. Notice that there are two completely interchangeable ways to define the term fundamental frequency. In the time domain, the fundamental frequency is the number of cycles of the complex pattern that are completed in 1 second. In the frequency domain, except in the case of certain special signals, the fundamental frequency is the lowest harmonic in the harmonic spectrum. Also, the fundamental frequency defines the harmonic spacing. That is, when the fundamental frequency is 100 Hz, harmonics will be spaced at 100 Hz intervals. That is, 100, 200, 300. When the fundamental frequency is 125 Hz, harmonics will be spaced at 125 Hz intervals, that is 125, 250, 375, and when the fundamental frequency is 200 Hz, harmonics will be spaced at 200 Hz intervals, that is 200, 400, 600. For some special signals, this will not be the case. There are some complex periodic signals that have energy at odd multiples of the fundamental frequency only. A square wave, for example, is a signal that alternates between maximum positive amplitude and maximum negative amplitude. The spectrum of square waves shows energy at odd multiples of the fundamental frequency only. Also, a variety of simple signal processing tricks can be used to create signals with harmonics at an arbitrary set of frequencies. For example, it is a simple matter to create a signal with energy at 400, 500 and 600 Hz only. While these kinds of signals can be quite useful for conducting auditory perception experiments, it remains true that most naturally occurring complex periodic signals have energy at whole number multiples of the fundamental frequency. So, when fundamental frequency is low, harmonics will be closely spaced, and when fundamental frequency is high, harmonics will be widely placed. This is clearly seen in the figure 3.11. The signal with the lowest fundamental frequency, 100 Hz, the middle signal shows the narrowest harmonic spacing, while the signal with the highest fundamental frequency, 400 Hz, the bottom signal, shows the widest harmonic spacing. Figure 3.12. Time and frequency domain representations of three non-transient complex aperiodic signals. Unlike complex periodic signals, complex aperiodic signals show energy that is spread across the spectrum. This type of spectrum is called dense or continuous. These spectra have very different appearance from the picket fence look that is associated with the discrete harmonic spectra of complex periodic signals. There are certain characteristics of the spectra of complex periodic sounds that can be determined by making simple measurements of the time domain signal, and there are certain other characteristics that require a more complex analysis. For example, simply by examining the signal in the bottom panel of figure 3.11, we can determine that it is complex periodic. That is, it is periodic but non-sinusoidal. And therefore, it will show a harmonic spectrum with energy at whole number multiples of the fundamental frequency. Further, by measuring the fundamental period 2.5 milliseconds and converting it into fundamental frequency 400 Hz, we are able to determine that the signal will have energy at 400, 800, 1200, 1600, etc. But do we know the amplitude of each of these frequency components? And how do we know the phase of each component? The answer is that you cannot determine harmonic amplitudes or phases simply by inspecting the signal or by making simple measurements of time domain signals with a ruler. We will see soon that a technique called Fourier Analysis is able to determine both the amplitude spectrum and the phase spectrum of any signal. We will also see that the inner ears of humans and many other animals have developed a trick that is able to produce a neural representation that is comparable in some respects to an amplitude spectrum. We will also see that the ear has no comparable trick for deriving a representation that is equivalent to a phase spectrum. This explains why the amplitude spectrum is far more important for speech and hearing applications than the phase spectrum. We will return to this point later. Figure 3.13. Time and frequency domain representations of three transients. Transients are complex aperiodic signals that are defined by their brief duration. Pops, clicks, and the sound gun fire are examples of transients. Figure 3.14. Illustration of the principle underlying Fourier analysis. The complex periodic signal shown in panel was derived by point-for-point summation of the sinusoidal signals shown in panels A to D. Point-for-point summation simply means beginning at time 0, that is the start of the signal, and adding the instantaneous amplitude of a signal A to the instantaneous amplitude of signal B at time 0, then adding that sum to the instantaneous amplitude of signal C also at time 0, then adding that sum to the instantaneous amplitude of signal D at time 0. The sum of instantaneous amplitudes at time 0 of signals A to D is the instantaneous amplitude of the composite signal at time 0. For example, at time 0, the amplitudes of sinusoids A to D are 0, plus 100, minus 200 and 0, respectively, producing a sum of minus 100. This agrees with the instantaneous amplitude at the very beginning of composite signal E. The same summation procedure is followed for all time points. An aperiodic sound is any sound that does not show a repeating pattern in its time domain representation. There are many aperiodic sounds in speech. Examples include the hissy sounds associated with fricatives such as F and S, and the various hisses and pops associated with articulatory release for the stop consonants B, D, G, P, T, K. Examples of non-speech aperiodic sounds include a drummer's cymbal or snare drum, the hiss produced by a radiator, and static sound produced by a poorly tuned radio. There are two types of aperiodic sounds. One, continuous aperiodic sounds, also known as noise, and two, transients. Although there is no sharp cutoff, the distinction between continuous aperiodic sounds and transients is based on duration. Transients, also pops and clicks, are defined by their very brief duration, and continuous aperiodic sounds are of longer duration. Figure 3.12 shows several examples of time domain representations and amplitude spectra for continuous aperiodic sounds. The lack of periodicity in the time domain is quite evident. That is, unlike the periodic sounds we have seen, there is no pattern that repeats itself over time. Figure 3.15. A signal enters a Fourier analyzer in this time domain and exits in the frequency domain. As outputs, the Fourier analyzer produces two frequency domain representations: an amplitude spectrum that shows the amplitude of each sinusoidal component that is present in the input signal, and a phase spectrum that shows the phase of each of the sinusoids. The input signal can be reconstructed perfectly by summing sinusoids at frequencies, amplitudes and phase that are shown in the Fourier amplitude and phase spectra using the summing method that is illustrated in figure 3.14. All aperiodic sounds, both continuous and transient, are complex in the sense that they always consist of energy at more than one frequency. The characteristic feature of aperiodic sounds in the frequency domain is a dense or continuous spectrum, which stands in contrast to the harmonic spectrum that is associated with complex periodic sounds. In a harmonic spectrum, there is energy at the fundamental frequency, followed by the energy at the second harmonic, followed by another gap, and so on. The spectra of aperiodic sounds do not share this picket fence appearance. Instead, energy is smeared more or less continuously across the spectrum. The top panel in figure 3.12 shows specific type of continuous aperiodic sound called white noise. By analogy to white light, white noise has a flat amplitude spectrum, that is, approximately equal amplitude at all frequencies. The middle panel in figure 3.12 shows the sounds and the bottom panel shows the sound. Notice that the spectra for all three sounds are dense. That is, they do not show the picket fence loop that reveals harmonic structure. Figure 3.13 shows domain representations and amplitude spectra for three transients. The transient in the top panel was produced by rapping on a wooden desk. The second is a single clap of the hands, and the third was produced by holding the mouth in a position for the vowel O and tapping the cheek with an index finger. Note that brief durations of the signals. Also, as with continuous aperiodic sounds, the spectra associated with transients are dense. That is, there is no evidence of harmonic organization. In speech, transients occur at the instant of articulatory release for stop consonants. There are also some languages such as the South African languages Zulu, Hottentot and Xhosa that contain mouth clicks as part of their phonemic inventory. Mackay, 1986. Fourier analysis is an extremely powerful tool that has widespread applications in nearly every major branch of physics and engineering. The method was developed by the 19th century mathematician Joseph Fourier, and although Fourier was studying thermal waves at the time, the technique can be applied to the frequency analysis of any kind of wave. Fourier's great insight was the discovery that all complex waves can be derived by adding sinusoids together, so long as the sinusoids are of the appropriate frequencies, amplitudes and phases. For example, the complex periodic signal at the bottom of figure 3.14 can be derived by summing sinusoids at 100, 200, 300, 400 or 500 Hz, with each sinusoidal component having the amplitude and phase that is shown in the figure. See the caption of figure 3.14 for an explanation of what is meant by summing the sinusoidal components. The assumption that all complex wave can be derived by adding sinusoids together is called Fourier's theorem, and the analysis technique that Fourier developed from this theorem is called Fourier analysis. Fourier analysis is a mathematical technique that takes a time domain signal as its input and determines 1. The amplitude of each sinusoidal component that is present in the input signal, and 2. The phase of each sinusoidal component that is present in this input signal. Another way of stating this is that Fourier analysis takes a time domain signal as its input and produces two frequency domain representations as output. 1. An amplitude spectrum and 2. A phase spectrum. The basic concept is illustrated in figure 3.15, which shows a time domain signal entering the Fourier analyzer, emerging at the output of the Fourier analyzer is an amplitude spectrum, a graph showing the amplitude of each sinusoid that is present in the input signal, and a phase spectrum, a graph showing the phase of each sinusoid that is present in the input signal. The amplitude spectrum tells us that the input signal contains one 200 Hz sinusoid with an amplitude of 100 Pa, a 400 Hz sinusoid with an amplitude of 200 Pa, and a 600 Hz sinusoid with an amplitude of 50 Pa. Overtones versus harmonics. The term overtone and the term harmonic refer to the same concept. They are just counted differently. As we have seen in a harmonic series such as 100, 200, 300, 400, etc., the 100 Hz component can be referred to as either the fundamental frequency or the first harmonic. The 200 Hz component is the second harmonic, the 300 Hz component is the third harmonic, and so on. An alternative set of terminology would refer to the 100 Hz component as the fundamental frequency, the 200 Hz component as the first overtone, the 300 Hz component as the second overtone, and so on. Use of the term overtone tends to be favored by those interested in musical acoustics, while most other acousticians tend to use the term harmonic. Octaves versus harmonics. An octave refers to a doubling of frequency. So, if we begin at 100 Hz, the next octave up would 200 Hz, the next would be 400 Hz, the next would be 800 Hz, and so on. Note that this is quite different from a harmonic progression. A harmonic progression begins at 300 Hz would be 300, 600, 900, 1200, 1500, etc. While an octave progression would become 300, 600, 1200, 2400, 4800, etc. There is something auditorily natural about octave spacing, and octaves play a very important role in the organization of musical scales. For example, on a piano keyboard, A above middle A6 is 808 Hz, A7 is 1, 760, and so on. Wavelength. The concept of wavelength is best illustrated with an example given by Small, 1973. Small asks us to imagine dipping a finger repeatedly into a puddle of water at a perfectly regular interval. Each time the finger hits the water, a wave is propagated outward, and we would see a pattern formed consisting of series of concentric circles. See figure 3.16. Wavelength is simply the distance between the adjacent waves. Precisely the same concept can be applied to sound waves. Wavelength is simply the distance between one compression wave and the next, or one refraction wave and the next, or more generally, the distance between any two corresponding points in adjacent waves. For our purpose, the most important point to be made about wavelength is that there is a simple relationship between frequency and wavelength. Using the puddle example, imagine that we begin by dipping our finger into the puddle at a very slow rate, that is, with a low dipping frequency. Since the waves have a long period of time to travel from one dip to the next, the wavelength will be large. By the same reasoning, the wavelength becomes smaller as the dipping frequency is increased. That is, the time allowed for the wave to travel at high dipping frequency is small, so the wavelength is small. Wavelength is a measure of distance, and the formula for calculating wavelength is straightforward algebraic rearrangement of the familiar distance is equal to rate time. Formula from junior high school is equal to C by F, where wavelength C the speed of sound, F frequency. Wavelength is measure of the distance between the crest of one cycle of a wave and the crest of the next cycle, or trough to trough, or in fact the distance between any two corresponding points in the wave. Wavelength and frequency are related to one another because the wave has only a short time to travel from one cycle to the next. High frequencies produce short wavelengths. Conversely, because of the longer travel times, low frequencies produce long wavelengths. For our purpose, it is not important to understand how Fourier analysis works. The most important point about Fourier's idea is that, visual appearances aside, all complex waves consist of sinusoids of varying frequencies, amplitudes and phases. In fact, Fourier analysis applies not only to periodic signals such as those shown in figure 3.15, but also to noise and transients. In fact, the amplitude spectra of the aperiodic signals shown in figure 3.13 were calculated using Fourier analysis. In later chapters, we will see that the auditory system is able to derive a neural representation that is roughly comparable to a Fourier amplitude spectrum. However, as was mentioned earlier, the auditory system does not derive a representation comparable to a Fourier phase spectrum. As a result, listeners are very sensitive to changes in the amplitude spectrum, but are relatively insensitive to changes in the phase. Thank you.